Now that we know how to get the equation of a line in three-space in parametric form, let's see how we can relate two lines, the different relationships two lines can have. In general, the parametric form of a line, the parametric equation for a line, tells us two things. It tells us a point on the line, and it tells us a vector that determines the direction of the line. Well, for two lines to be parallel, they need to travel in the same direction. So two lines that have the same direction will be parallel. However, that doesn't mean we need them to have the same vector. Let's suppose we have a line that moves in the direction 5, -2, 3. And we have another line that moves in the direction 10, -4, 6. These both move in the same direction, although they are a different length. This second one is twice as long. However, the length of the vector does not matter, only the direction. So multiplying a vector by a scalar does not affect the direction of the line. The length of the line is infinite, so the length of the vector determining the line doesn't matter. So both of these are the same direction. These lines would be parallel. So as long as our vectors are multiples of one another, we can say that our lines are either parallel or possibly the same. The first thing I want to show and look at are how to tell if two lines are the same. As we saw in the previous video, parametric equations for a line are not unique. So in order to be the same, first off, we need them to be traveling in the same direction. This is the easiest thing to check. And we also need them to share some points. In particular, all of their points. But since they're traveling in the same direction, we only need to show they share one. If they share one, then they intersect. But if they're in the same direction, they must be parallel. So the only way for them to intersect and be parallel would be the same. So in order to do this, I'll find a point on one of the lines and show it also has to be on the second line. So let's look at an example of this. Let's consider these two lines. 6 minus 5t for x, y is -3 plus 3t, and z is 3 minus 6t. My second line, x is 1 plus 10t, y is -6t, and z is -3 plus 12t. The direction comes from the coefficients of t, since the general form of a line is point plus t times direction. So the direction of this first line would be -5, 3, -6. The direction of the second line would be 10, -6, 12. And I can see that these are scalar multiples. If I were to multiply this first one by -2, I would get the second one. So they do travel in the same direction. The next thing I need to show is that they share at least one point. For the first line, I'm going to let t be equal to 0. That'll give me the point 6, -3, 3. Since it'll just give me these coefficients, since all of the t terms will disappear. And what I want to know is this point on my second line? Well, these are x, y, and z, so I'm going to use my second line. X, or 6, should be equal to 1 plus 10t. If I solve this, I get 1/2 is equal to t. Y is -3. in my point, and in my second line, y is negative 6t. If I solve this, I get 1/2 equal to t. The point says z is equal to 3. The line says negative 3 plus 12t. And if I solve this, I once again get 1/2 t. And the fact that all of these are the same tells me that yes, this point is on this line. If any one of these was different, then the point would not be on the line. But since we have that they travel in the same direction and they share a point, these two equations, these two parametric equations, represent the same line. Even though they look very different and they're written in different forms, they do represent the same line since they're traveling in the same direction and share points. As another example, let's look at the lines defined by x equal to 5 minus t, y equal to negative 1 minus 3t, and z equal to negative 2 minus 2t. And the line x equal to negative 5 minus 3t, y equal to negative 2 minus 9t, and z equal to negative 6t. The direction of my first line is negative 1, negative 3, negative 2. It comes from my coefficients. My second one is negative 3, negative 9, negative 6, once again coming from those coefficients. I can see that multiplying the first one by 3 gives me the second one, which tells me they are traveling in the same direction. So the question is, are they the same? If I let t be equal to 0 in the first line, I get x is 5, y is negative 1, and z is negative 2. So, setting pieces equal, I have x equal to 5 and x equal to negative 5 minus 3, 2. So 5 equal to negative 5 minus 3t. And if I solve this, I get negative 10/3 is equal to t. For my y's, I have negative 1 from my point sticking in 0. And from my equation for the second line, negative 2 minus 9t. And when I solve this, I get negative 1 over 9. And I can stop there and say that this point is not on this line since I got two different values of t. In order for them to share a point, I need to get the same value of t for each one of my equations. I don't even need to check z here because I know that this point is not on the second line. So these lines are in the same direction, but they do not intersect. And so these will be parallel since they are in the same direction, but they don't intersect. Finally, let's consider the line x equal to negative 1 plus 4t, y equal to 3 minus 4t, and z equal to negative 4 plus t, and the line x equal to negative 2 plus 3t, y equal to negative 11 plus 2t, and z equal to negative 5 plus t. The direction for my first line is 4, negative 4, 1. And the direction for my second line is 3, 2, 1. And I can see that there's nothing I could multiply the first vector by to get the second vector. So these do not go in the same direction. These lines have two separate directions. So since they have different directions, my next question is, do they intersect? Or are they skew lines? And if you've never heard this term, skew lines are lines that do not intersect, but also do not travel in the same direction. So in order to see if they intersect, I'm going to need to see if they share a point. When I was looking if lines were the same, I was able to plug in t equal to 0 for one equation and substitute it in and see if I could get a solution. But this won't work that way. I need to show they intersect at some point, but I don't know what point that is. What I need to do is take my x for my first equation and set it equal to -2 plus 3s. I need to use a different letter. I don't need the value of t to be the same in both of the lines, so I'm going to use an s in my second equation. My y from my first equation is 3 minus 4t. My y for my second equation is -11 plus 2t, so I'm going to write it as -11 plus 2s. My z is -4 plus t for the first line. My second line is -5 plus t, so I'm going to write it as -5 plus s. Now I have a system of equations, and we need to solve this. You can do this by hand or use a computer or a calculator to solve this. But if you do, you get t equal to 2 and s equal to 3. Since I got a solution, they do in fact intersect. If I would have gotten no solution here, they would not intersect, but I did get a solution. And in fact, I can tell exactly where it is. I can plug t equal to 2 into my first equation, my first line. So I have -1 plus 4 times 2, which is 7. For y, I have 3 minus 4 times 2, which is -5. And for z, I have -4 plus 2, which is -2. So these intersect at 7, -5, -2. Alternatively, I could have used s equal to 3 in my second equation, my second line. I would then have x equal to -2 plus 3 times 3, which is 7. I would have y equal to -11 plus 2 times 3, which is -5. And I would have z equal to -5 plus 3, which is -2. So I can see I did in fact get the same point because this is the point where these lines intersect.